So in Unit 3, we're going to be talking about functions and graphing. So for mathematical functions, we have what is called f of x, where we're given an x, we'll plug it into the function, and then we get an output of an answer. A lot of times students see f of x and they think that it's f times x. That's not what it means. It's just when you have f and then have in parentheses x, I'm going to give you a number that you plug this number in for every x that you see in the function, and then you get your output of what the answer should be. So here's a quick example. For f of x, I'm giving you that x is equal to 3. So if I plug 3 in for this x and this x, add 12, I'll get the answer to be negative 30. Be careful when you're working in your calculator. You want to actually, for this particular one, put the 3 in parentheses and then put negative and then square on the outside, because a lot of times without using parentheses, when it comes to negative numbers, you get two different answers. So because this 3 is positive, in parentheses you put a positive 3. If it was a negative 3, then in parentheses put the negative when you're dealing with the square, so you can get your problems accurate. So pretty much, what is a function? A function is pretty much, if I look at it, that you have an independent variable that corresponds to your unique dependent variable. And we kind of think about about students when they want to go off to college, they want to be independent, but realize when it comes down to asking for money, needing money, and all that kind of stuff, then they depend back on their parents and they give them a call and say, "Can I have some money for such and such?" So in this two pictures here, we have a water with a flower with a plant, and then we have the number of songs and the cost of each song. So what is the independent and dependent variables in this problem? The independent variables is always going to be x, and then these two pictures, the water and the number of songs, is considered to be the x, because those are independent variables. So once again, there's nothing changing about the water. The water is what it is, and the number of songs, that's not changing on that certain CD that you have. You have that number of tracks on that one song. However, the dependent variable is going to be the plant and the cost, because the plant depends on the water as far as how it grows and have life and stays alive. The cost depends on the number of songs. So if you tell me 3 songs, it's going to be $3.87. If you tell me 10 songs, it's going to be $12.90. So X is going to be the independent, which again, that really much doesn't change. It kind of stays put. Independent means I'm on my own, or I'm not, nobody can tell me what to do. That's what I am. Dependent is where we talk about what it depends on. So it always depends on the X. Now we're going to go in what is called a vertical line test for graphs. So basically, I'm going to provide you with some graphs, and you need to tell me, is these graph A, B, C, or D, is it a function or is it not a function? And you determine this by drawing a vertical line straight through the graph. Each one of these graphs, it doesn't matter where you draw the vertical line. It can be here, it can be here, over here, over here. But your key is you want to try to draw that line where you can actually get the graph to hit that line 2 times. So if you can draw it where it can hit it two times, that's our pretty much our goal to determine whether it's going to be a function or not. So if I draw my line here, this is considered to be a function. Why? Because how many times does this red line hit the blue line? You only see it hit it 1 time. If your answer is always 1, then we're going to get a thumbs up saying it is a function. This time I drew the line over here. How many times you see it? 1. 1 means yes, is a function. Here again, we drew it here. Again, when the question asks, is it a function? Yes, we did our vertical line test, hits it 1 time, function. However, the last one is not a function because it hits it 2 times. That means the x's repeat over here and here. We don't want x's to repeat when it comes to being a function. You only want one x. So when it goes to this x here, that's only 1 time. So this x is actually equal to this x. So if this x was -5, if we go over to -5, this point would be -5 something, and this would be -5 something down here. which means I have two x's that's opposite negative 5. That's not a function. So 2 or more means not a function. 1 time means it is a function. So quadrants. When we start quadrants in a graph, here is my x-axis going left and right. Here's my y-axis going up and down. This quadrant here, this quadrant in the top right-hand corner is considered to be number 1. We go to number 2, number 3, and number 4. These are the actual numbers that you need to replace the quadrant each time that you do when you look at a graph. 1, 2, 3, and then 4. If we need to plot points, we always want to start with the x first. These are called ordered pairs, x and y. The x is always what you start first. On the x-axis, you go to -4. So 1, 2, 3, 4. Here's my -4 here. So just hold it right there. We're not drawing anything. Just kind of hold this spot right here at -4. And now we got to go on the y to 1. And that's because it's positive, we're going to go up 1. So we go to -4, go up 1. Then we draw a little dot like so. And that'll be this first point. This one here is 3, 5 because we go over 1, 2, 3, and then up to 1, 2, 3, 4, 5. So here's a little point we draw here. So again, we plot the x's first and then the y second. If it has 0, we don't move any. We don't go left and right, or we don't go up and down. We draw a little, and this is called the origin when it's right at the middle. So here we want to create a rectangle, a perfect rectangle as far as the point. So here's -1, 1. So go over 1 and down 1. This is -1, 1. -1, 2. So go over 1, up 2. And then 3, 2. 1, 2, 3, up 2. And the last one was actually missing. So if you actually look in the blank, if you go to my Moodle page and go to the blank notes, you notice that we're missing a point here because I only gave you 3. So what is the fourth point they're going to make to make this a perfect rectangle? So we already know it needs to come over to 3, and it actually needs to go into -1. So this makes it 3, -1 to make a finish off our coordinates for the fourth vertex. Using the calculator to graph linear functions, the first thing you do anytime you're given a linear function, which is pretty much in the form of y equals mx plus b. So all equations need to have the y by itself, m stands for slope, your x and y are your ordered pairs, and b is the y-intercept. Y equals mx plus b. That means all the numbers and x's need to be on the right side, and we just need to have x of the y by itself. If your y is by itself in your equation, you can go ahead and place it into your calculator by hitting the y equals here. Hit y equals, then we hit 2. The x is located right here, minus the 1. This is then if you want to look at some ordered pairs in order to graph it on MyMathWise+, we'll hit second and then graph, and it brings up a table. You want to pick the ordered pairs that are the smallest or pretty much easier to graph that's going to fit into your graph that you have placed in front of you. So you can pick 0, -1, or you can pick -1, 3. All you need from MyMathWise+ is 2 ordered pairs. Once you get those 2 ordered pairs, you can plot and then connect the dots in MyMathWise+ when you're doing your homework. If you want to see what the picture looks like, you can either hit graph, or I will always suggest you always hit Zoom 6. Zoom 6 always takes your calculator back to the default or the original standard looking graph of what it should look like. So Zoom 6 is what the graph should look like. So this should match what you draw on your paper or in MyMathWise+ when you're doing your homework. Now, how to find a domain. Now this part here can be really complicated at times, but hopefully when we go through these 3 cases, you'll know how to find the domain. These are 3 cases that you will see when you know there's going to be actually a problem, or I would consider to say a red flag. If you don't see a fraction, a square root, or a fraction in the square root, the answer for domain is always going to be all real numbers. That's never going to change. So you look at your equation, any equation that's given to you. If you don't see a fraction, a square root, or a fraction and a square root together, the answer you can write down is all real numbers. All real numbers are indicated by saying negative infinity to positive infinity, meaning that any number that you provide me with in between negative infinity, that's pretty much all the numbers. Any number that you pick from negative infinity to positive infinity, any number in between that you choose and you plug into any equation given, you're always going to get some answer. It can be a negative answer, it can be a square root, I'm sorry, it can be a decimal, or it could be a fraction. That doesn't matter to us. So long as it's giving you some kind of an answer for any number that you choose. That's why it's called all real numbers. However, when you run into these three cases, a fraction or even roots or square root or both, there's going to be some numbers that's going to cause these going to give us red flags, or what is called a red. Another word for red flags for mathematical terms is undefined. So let's talk about fraction. If you notice anything about a fraction when working with fractions, if you have a zero on the bottom, so 3 divided by 0, that the answer will give you undefined. If you put in your calculator, it's going to give you an error. You cannot do 3 divided by 0. That's just impossible to do. So what number is going to cause this little function expression down here to equal 0? So in order to do that, we just set the denominator equal to 0. Add 5 to both sides, and notice that x cannot equal 5, because why? If we say, we know that if x equals 5, it produces a 0, which we cannot have 0 on the bottom. So anytime you have a fraction, just set it equal to 0. It's just the denominator. We're not focused with anything to do with the numerator when it comes to domain. Just the denominator, and the domain deals with the x values only. So we don't pay attention to the y. Range, what we get into a bit later, that's up and down for the range as far as y's. Domain is strictly left and right x values. So for here, you can have all the numbers, any number that you choose, except for -5. So we can go from negative infinity to 5. So we put parentheses around both of those for comma in the middle. Union 5 to positive infinity. That's called the integral that we're going to that you use for figuring out what the domain is. The next case is going to be if you see the square root. The rule is with square roots is you cannot have, or you cannot take the square root of a negative number. So whatever this answer is here, x plus 3, it must be greater than 0. Why does it must be greater than 0? If you look at the number line, all the numbers that's greater than 0 are positive answers, or positive numbers. A positive number means that you can take the square root of that. It does not matter if the number is not a perfect square. Like if I say the square root of 4 is 2, but I say the square root of 2, it doesn't give you a clean or perfect square root, which is fine. That's not our concern. Our concern is to make sure that result is positive. So what we need to do is figure out what makes this equation here, this function here, have a negative inside. So we set this part greater than or equal to 0. Yes, it can still equal 0. That's not an issue because 0 is neither positive or negative. We're looking for negative numbers. So we add 3 to both sides. Now this is saying you can choose any number that you want, but the number cannot be greater than or equal to 3. It's just that's here, because any number that's greater than 3, when we plug it in here, it's going to give us a true answer, which says that's what we want. Any other number that we choose that's going to be either less than -3 is going to give us a negative in here, and that gives us the red flag, which means imaginary or undefined. So again, any number that's greater than -3, that's what we want. So the domain for this one is -3 to positive infinity. The last part here is this time here, since it's on the bottom, it can't be a negative in the inside like we described here. And because it's in the denominator, it also cannot be a 0. So this is how we get rid of this little equal sign right here, greater than equal to, and just say greater than, because it needs to be just positive. It can't be equal to 0. Set just the denominator here, greater than 0, add 2 to both sides. Any number that you choose that's greater than 2 is going to make this here not be undefined. So that's good. That's what we want for this one as far as our domain. So here are 3 examples that I'm going to actually work out for you. And we need to figure out the domain for each one of these. So for the first one here, remember, all we're really doing is just focusing on the denominator, and we're going to set the denominator x minus 8. It has to be greater than 0. Cannot be equal to 0 because, again, it's located in the denominator. So we set this plus 8, we do plus 8. We have x can be greater than 8 in this case. So our domain for this one is going to be 8, comma, infinity to positive infinity. So 8 in this case, all the numbers greater than 8 will work when we plug it in for here, and we won't get a red flag for it. The next one here is the same thing here, but this time here, it can be set equal to 0 this time. So it can be greater than or equal to 0 because 0 can be, you can take the square root of 0, which is 0 in this case. So plus 54 plus 54 on this one. This side cancels out. So we have 3y is greater than 54. If we divide both sides by 3, we get 18. So here, y can be greater than or equal to 18, and this one up here will work. So this is just a side note that you can want to write down. If we were dividing both sides by a negative number, so say that this was a -3, we had to do -3, -3, then this inequality sign gets flipped. So this is just a little side note that you can write down in your notes. Anytime you divide by a negative number, remember to flip the inequality sign. That's only when you're dividing by a negative. So if there's no negative, there's nothing for you to do. You can just keep it exactly the same, and that would be our answer. The last one here, the only thing we need to do for this one is just set it equal to 0 because we don't want 0 to be on the bottom. So -7, 5x is equal to -7. Divide both sides by 5. So x cannot equal 7/5. So here's what the domain should look like for this one. We go from negative infinity, because that's the lowest one, to -7/5 union, and we go from -7/5, comma, infinity. So that's what the interval should look like when we're writing for the domain. So these are the answers for domain. I didn't write the interval for this one, so it's going to be 18 to positive infinity. So these are considered to be the domains for these particular problems. So here, just another recap. Again, if you look at this one here, the reason why it's all real numbers, you can just write a big R with a little dark, really dark or bold R. Let us know that it's going to be all real because there's no fraction, there's no square root. So we can just say any other time you see if the domain for a polynomial function is going to be all real because it doesn't fall into them other 3 cases. Here we have the square root, so we know we have to set it greater than or equal to 0. And then here we just set the bottom part equal to 0 to figure out what the domain is. Here are some additional videos as far as if you need some additional assistance with domain and range. Now let's move towards defining what a piecewise function looks like. So piecewise function is just pretty much what the name is. It's pieced together. So you have maybe a line that goes up here, then stops and goes this way, and then comes down and goes this way. So you have like 3 pieces, and this is pretty much where the lines get drawn from: x plus 1, 5, and x squared. Those are my 3 functions that I can draw. However, I just need a piece of it. I don't need the full length of x plus 1. So if we have x plus 1 in our calculator, so x plus 1, we hit zoom 6. This is the full length of x plus 1. But in our example, we don't need the full length. All I'm really focusing for is for when x is less than negative 2. So looking at this graph here, here's my negative 2. And the only thing I'm focusing on is anything to the left of negative 2. So all this over here. So all this right here I'm going to keep. And if you had an eraser, you can erase these lines over here because you don't need this line. Because for piecewise, I'm only taking a piece of this blue line. So only from this negative 2 part here onto the left is the only part I'm actually going to graph when I finish off my graph. The next one is x equals to y equals to 5, and all these are y equals. This f of x is the same thing as saying y. So y equals x plus 1, y equals 5, and y equals x squared. So going back to our calculator, if I just put in for this number 2, 5, and then hit graph. So here, I don't need this full length here. I just need a piece of it. So what piece I'm going to look at? All I want the numbers is between negative 2 and 3. So the only red part of the line is from negative 2, which we stop right here from negative 2 here to positive 3. So from here all the way to here is the only part I'm actually keeping. So you can scribble out and erase on both sides of it. So I got from here to negative 2, jump up here to negative 2 to 3, and let's figure out what the last part should look like. And that's going to be x squared. So last one here, we go x squared. So here's the x squared one. So which part are we actually looking for here? I want anything greater than 3. So let's go to 3. 1, 2, 3. Here's my 3. So anything greater than 3 is all these points over here. So I make my little marker maybe about right here, and then from here on up, you know, it continues on forever in this direction, going up here. It's the only part I'm keeping. So the rest of it I get rid of. So from here to negative 2 is what I keep. Jump up here from negative 2 to 3 for the red, and then from right here to on up is what I'm going to keep, and for that's what your graph is going to look like. Everything else you can erase off your graph. That's what a piecewise function actually looks like as far as graphing. Now, if we need to define the function, if I gave you negative 5, it's up to you now to pick which function should I use, x plus 1, the 5, or x squared. Where can I plug this x into? You don't need to plug it in here because there's no x's. But where can I plug this negative 5 into? This one or this one? Well, you have to look at the part over here where it actually makes it true. Is negative 5 greater than 3? Can we say negative 5 is greater than 3? I don't think so. So we can put an X on this one because I'm not using this one. Negative 5 is not in between negative 2 and 3 also. So we can get rid of this second part. The only one this one works for is the first one because X or negative 5 is less than negative 2. So this is the one we're actually going to use. And how do we use it? We'll plug this negative 5 only into this function up here. Negative 5 plus 1, get our answer to be negative 4. That's going to be the answer for this function. Same thing goes for this one, negative 3. We plug negative, we figure out which one it should go to. The first one, second one, and the third one. Negative 3 only works with the first one. Plug it in here, get our answer. 0. Which one does 0 work for? This one, this one, and this one. Well, the only one that works for it is this one because 0 is in between negative 2 and 3. So because 0 is in between here, there is no x in this portion here to actually plug in. So the answer is just 5. So when it's just a lonely number or a constant, you don't have to worry about plugging in any x's. You just say the answer is going to be just that, whatever that number is. So in this case here, it'll be 5. 3, we can plug 3 into here because we can't plug it into here. 3 is not greater than 3. And 3 is not less than negative 2, but 3 is less than or equal to this 3. So again, the answer for this one just would be 5. So these two here is 5. 4, I will plug it into the last one because 4 is greater than 3 and 10 is greater than 3. So I'll plug 4 in here. 4 squared is 16. 10 squared is 100. So here's the math. We plug the -5 that we found, get our answer to be -4 and -2. Those are the answers for the first two. When we do our zeros, it's just 5. That's just in our answers. When we did 4 and 10, we get 16, and we get 100 to be our answer for the last part. So once again, looking at here, looking at your graph, when you're given a piecewise function and you're given your points, your x's, figure out which one you should go with by looking at the given parts on the side for here. So look at this point, see if it goes here. If it does, put it into that equation, get your answer. So looking at this one here, where does -4 go? Does it go to the first one or the second one? We have to say, does -4, is it less than or equal to 1, or is it greater than 1? I don't think it's greater than 1, so it will actually go to this one here, which means we plug it into the first one. So -4 plus 4 gives us what? 0. That's our first answer. 0 goes to this one here because it's less than 1. So 0 plus 4 is 4. The 1 also goes to the top one because 1 is less than or equal to 1 itself. So 1 plus 4 gives us the 5. And the last one, 3, is greater than 1, so we put it up here. 8 minus the 3 gives us the 5 here. Now let's talk about intercepts, x-intercepts. What is an x-intercept? An x-intercept is exactly what the terminology is when does the x, when you see the graph intercept the x-axis, and that's considered to be our zeros. So given this function here, the best thing that you want to do, especially when we go to our calculators, is you want to make sure on this side of the equal sign is all our numbers, and on the right side is just a 0. So we need to move this 10 over to this side by doing the opposite, which is subtract. That way the right side is equal to 0, and we have everything else on the left side. This is going to be helpful when we put it into our graph to figure out what our zeros are. Those of you that's familiar with factoring, you can factor these two to also get your zeros by getting our two factors and send them equal to 0. You can do it that way. But once you do get it to this side equal to the function, this side equal to 0, we hit the top left-hand corner, y equals. Type in y1, the first equation. So the left side is considered to be y1. So put into y1, x squared plus x 3x minus 10. The right side of the equal sign, that's considered to be our 0, so you just type in 0. Then you hit zoom 6. If these numbers were a lot bigger, then you would actually hit for this one zoom 0 because the calculator will actually fit the graph inside your little window for your calculator. But if the numbers are relatively small, zoom 6 should be efficient enough for you to use. Then look at the parabola. The parabola has either a parabola going upward or opens downward. How many times do you see that parabola intersect? That's what we're trying to find, intersect the x-axis. For this one here, we said 2. The reason why we said 2 is because the highest degree up here is 2. So that's how many times it actually is going to hit the x-axis is 2 times. The highest degree will give you that answer. So then we hit second trace number 5. Move your cursor, the little blinking cursor, to the left where you see both the graph and the x-axis hit, and you hit enter 3 times. Then to get the other side, don't slide over to the other side. You have to hit second trace number 5 again, and then you get your answer for that one. Do it again, and then hit the enter 3 times. So just to give you an idea, I'm going to show you in the calculator how to do this one. So we have x squared plus 3x minus 10. That's the first equation for y1. The second one, we're going to put 0. Now, for my calculator, I have color coordinated because it's a 84 plus. Those of you that has the TI-83, you won't have two different colors, but just know that there are two lines when you graph the zero and then a function. Zoom 6. So in your TI-83, you'll have a black line that goes here and then another black line that goes across here. It's just you won't be able to see it because the x-axis and the line will blend itself together. But just know that we have two different lines, a blue and a red. So here's our first answer because it intersects the x-axis here, and then here's our second answer and it intersects it here. We hit second trace and we go down to number 5 because we're looking for the intersect. Here's my little blinking cursor. If you don't see it, focus on the Y and understand where it is. So right here, you don't see it, but you notice that I need to come up. So my numbers need to get bigger, and it does to my positive side. So here you get close enough to it. Now this one here actually gives it to it, but if you get somewhat near it and hit enter 3 times, 1, 2, 3, it gives you the answer of the intersection to be -5, 0. Make sure you always put these intersections in ordered pairs. Don't just write the answer to be -5 for the x-intercept. It needs to be presented in a ordered pair. So you'll put parentheses, -5, comma, 0, close parentheses. So once again, don't just take this little side thing and just slide it over here. You have to hit second trace, number 5. It kind of resets the calculator to know that you're looking for the second intersection, which is on this side. Again, get it somewhere close. It doesn't have to be on it. If you get somewhere near it, it'll actually jump to the spark for you. 1, 2, 3. So this one here will be parentheses 2, comma, 0, close parentheses. So for this application here, what we're going to be focusing on what the vertex is. The vertex is when you have a parabola and then you see a change in direction. That's what is called the vertex. So it's going up, 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 up. It changed direction right at this peak and comes down. That's what is called the vertex. And how do we know we're looking for the vertex? Because the question asks for how long does it take the ball to hit the ground? Well, this one here is the highest point. So if the question asks which is actually going to be the next problem, that the example I'm going to show you, how high does how much time does it take to reach that the maximum point? Then we look for the vertex. In this case here, I want to know how long it will take the ball to hit the ground. So it hits the ground here. So just looking at the calculator that we had before, the example that we had in the calculator, the ground is actually going to be the red line going across the x-axis. So that's actually considered to be our ground. So I can keep the y equals 0 in this one here, but I'm going to change this next part into this equation here. So negative 16x squared. So negative 16x squared plus 32x plus 128. Let's give it one more check. 32x plus 128. So that's the equation it gives us because the building is actually 128 feet high. And we're standing on top of the building. We're going to throw an object, a ball, up into the air and see how long does it take it to hit the ground all the way down here. So if you hit, because these numbers are big, Zoom 6 is not going to work. The graph is just way too big. So it's kind of hard to see. Yes, we do see it here, but we kind of want to see that vertex up top. So this is where we can hit Zoom 0 and see how we can see the top part of the graph, and the calculator actually fits it to the window. Now, if you want to play around with it, you can, but this is perfect. We can figure out the intersection here. There's no need to do any changing. You can hit second trace number 5, but if you want to kind of change it around to get a full picture of it, you can mess with the window. We don't need the back part of the building, so we can start at 0. And then going to the second part here, I don't need to go underneath the ground, so that can stay at 0. And for the Y scale, we can probably make this just maybe a tad bit bigger. So let's just make it 2 and then see what the graph looks like. So here's my building. I got rid of the back part because I don't care. We don't have to throw the ball backwards. And then we don't need to go any further past the ground. So I can stop it here. So here's the building, throw the ball. I want to know if I put my stopwatch on, I throw the ball, how long does it take to hit the ground here? So second trace, number 5. So here I don't see my little blinking cursor, but I know it's all the way at the bottom. So I got to make sure I increase, make sure it gets smaller, bigger. And there's my little cursor here. So I can find out where to hit the bottom here. So hit enter 3 times, 1, 2, 3. And it's saying that at 4 seconds, it takes this ball when I throw it in the air to hit the ground at ground 0. So 4 seconds. X will be the time, Y will be the height. So the question asks, what does the ground represent? In other words, what are we looking for? We're looking for the ground when it represents the x-intercept, meaning the x will be the time, and then the y would actually be the height. And 4 seconds was the time. So here's the question, the other part of the question, where when would the ball reach the height of 320? So this is we want to know at a height of 320, what time will the ball reach it? So this is where we need to figure out what the vertex is. So the best thing you want to do is just move this over, again, because we want to set this equal to 0. Move this over and put the same equation once we move it over into our calculator. So let's do that right now. So for this one here, once we move that, move it over, we get negative 32. So once we move the 320 over by subtracting, 288 minus 320 gives us a negative 32. We put it in the calculator. You can try Zoom 6 first, but if you don't see a perfect graph that you need to see, then you can do Zoom 0. This looks pretty much good enough that we need. So we go up here and figure out what the vertex is. For the vertex for this particular one is we're going to hit second trace and we're going to hit maximum. Because we see the peak at a maximum, the vertex at a maximum point, then we're going to hit the maximum. So let's go to here. It says left bound. So we're going to go to where the vertex is, right in the center. And if you go to the left, maybe about 3 times, just click it about 3 times. It doesn't matter. You can click it, stop it here, hit left bound, hit enter. Let's go to the right side. So here's the vertex again. Let's go to the right side of it. So the right side will be anywhere over here. And then we can bypass guess, just hit enter. Don't worry about guess, just hit enter again. And then it shoots it right up to the top. For this one here, we have a negative 1.5, and then the answer for this one here would be 4. So for here again, that's going to actually be the maximum height. So for this question here is when will the ball here, but again, since we set it equal to 0, we're looking for that ground 0 again. So anytime you're looking for the vertex, you hit the second trace and then hit the maximum if you want to look at the maximum height that the ball is thrown up in the air. So anytime you see a problem that says what's the maximum height, where's the height reached at the highest point, we do our vertex. For this particular one here, again, we want to know when it hits the ground, again, because we set it equal to 0. In this case here, you will probably see 2 answers for this problem. You'll see 2 answers because, again, we see it hitting the ground this way and hitting the ground this way. And when will the ball actually reach at a height of 320? Well, if we figure out what the height is, remember the building is 288 feet high. So we go up here. This top part of here is 288. If we go up a little bit further, we know that right about here is maybe 320, right here and right here. So let's draw a line straight across, and it hits it 2 times, 1 time here and 1 time here. So when the ball is thrown in the air, it reaches the height of 320 right here at 1 second, and then again over here at 2 seconds. So 1 second it hits 320 as the height, and then when it comes back down, it hits the 320 again marker at 1 second and 2 seconds. So let's figure out what that's going to look like. So we go down here for the ground zero, we hit second trace, we go down to intersection, go down to where it hits it the first time, hit enter 3 times, 1, 2, 3, and then we hit second trace, number 5 again for the intersection, and hit it 2 times again, 1, 2, 3. So 1 second and 2 second. I know it's giving you negative answers, but we know we can't go back in time, but it's going to still be 1 and 2 for the X's going to be for this particular one. So we need to have positive answers for when it comes to time because we don't go back in time. So 1 and 2 as far as the seconds is concerned. If we want to graph this graphically means using your calculator. Again, we do exactly like we did before. Set the left side equal to y1. Again, try to move this over to the other side to make this side equal to 0. So put this in for y1, put this in for y2, and then we can do our second trace, number 5, hit enter 3 times, and it gives us 1.4 as the answer. Same thing from here. Let's move the 7 over by subtracting. Put this in our calculator. Be careful with the square root. Only have the x underneath the square root. So slide your calculator over, push over when you're ready to put in plus 3x minus 7. Hit enter 3 times. Go to second trace number 5. Hit enter 3 times, and we get our answer to be 1.88. So for the range, once you hit this and find out what the graph is, the range is, remember, going up and down. Domain was left and right, range is up and down. So my question is, how far down, we always start with down because that's the smallest number, how far down you see this graph go? It goes at, this is 1, this is 2 on the y-axis. So we go 1, 2, and it's going to go up to infinity. So how far down does it go? It goes all the way down to 2. So if you draw a imaginary line going across horizontally at 2, how far up does it go? And it goes up to positive infinity. And does it touch it at 2? Yes, it goes straight through 2. It touches it at 2, so that's why we put a bracket. We put infinity, we put parentheses around things that we don't actually touch because we can't actually touch infinity. So infinities always get parentheses. So the same one here, we graph it. We notice that it starts at the 1. So the lowest point on the y, again, I'm not focused on the x's. I know it goes over here to the negative 1 or 2, but again, we're focused on up and down. So it starts at ground 0 and goes all the way up, 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 all the way up, going up to infinity. So how far down does it go? To 0, and it touches it. And then from going to positive infinity with a parentheses. Notice this one here, how far down this one go? If you know this one here, it has 2 little arrows, one at the bottom, one at the top. How far down does it go? Well, it kind of goes down forever. So that's why we notify this to be negative infinity. It just keeps going down, down, down. How far up does it go? It goes to positive infinity. So the range for this one is from negative infinity to positive infinity. So this, the last part we're going to talk about is going to be vertical translation. This is how we're going to take a graph and we're either going to shift it up, down, to the left, or to the right when it comes to translation or shifting, transformation. So looking at this one, if I'm giving you a function and we have a number with on the outside of the function that's kind of away from the x, when we look at the function, then we're going to shift it up this many units with a plus sign. If it's a minus, we're going to shift it down that many units. So here's an example. Here's our original function, 1/5 x to the 4th. If you see that the plus sign is on the outside, just like we notified here, here's our function. And then we put plus 5. That means we take the black one, which is this one here, and we shift it up 5. 1, 2, 3, 4, 5. So it goes up 5. If I have the same function here, but I have a -3, then we know we shifted going down. So here's the black one original. We go down 3. 1, 2, -3. So here that we have -3, as far as our shifting is concerned, we go, if it's located on the outskirts of the function, on the outside of it, away from the x, then we go up and down. Positive means up for vertical, negative, the minus means goes down for vertical. This time a horizontal shift. This time the number is inside with the x. If it's right beside or inside with the x, we're going to do the opposite of what the sign is by shifting. So a minus actually means we shift right. Well, it's kind of confusing because you think of going to the right being positive. In this case here, we have a minus. You have to do the opposite for horizontal translation. For the plus sign, we're going to go to the left. Here's our function again. This time, we're going to put -3 inside where the fourth root is, or by the x. -3 means, again, we go to the right 3 times. So take it 1, 2, 3, and move it to the right. Here we have the same function. We have a +7. That means we go to the left 7 times. So 1, 2, 3, 4, 5, 6, and then 7. We shift to the left 7. If we have a negative in front of the whole function itself, then it reflects across the x-axis. If the negative is inside with the x, it reflects on the y-axis. So here's an example of flipping over the x-axis. If you take this and kind of flip it down over the x-axis, it looks exactly the same. And because then we have a positive here and the negatives on the outside of the function, we flip it across the x-axis. This time I'll put the negative inside with the x. So every x here gets a negative. Here's our original one. So I'm putting a negative in front of here, negative in front of here, like I did here. And this here, the black one, represents the original. And it flips across this way, across the y-axis. So negatives inside you see flips across the y-axis. Negatives on the outside flips across the x-axis. So here's a little recap of what we just did as far as left, right, up, and down. So here I'm giving you the equation, and I want you to tell me what the equation looks like if I have the equation y equals 3x, and it needs to shift up. Here, and this one needs to shift left 2, this one needs to shift down and to the right 1. So if I need to shift up 1, remember up, vertical, the number needs to be on the outside away from all this stuff. So we have x plus 1, nowhere near the x. If I need to shift to the left 2, that means the left, this 2 needs to go inside with the x. So we have to put in parentheses x plus 2. Remember, left is opposite when I'm going left and right. And then put the square up there. So -2 is still on the outside. Put the plus 2 to make sure shift to the left. And then drop out the square back up there. This way we need 2 things, shift it down and shift it to the right. If I'm shifting to the right, it goes in the inside with this square root. I'm in the square, so we put this in parentheses. If I'm shifting down, it goes on the outside of this whole thing, on the outside here. So looking at here, we have x minus 1 in parentheses. That means it went to the right 1 time. Squared plus 4, and then now I need to shift it down 2. So the -2 goes on the outside. It does not go underneath the square root. It goes all away from the whole function itself, -2 outside by itself. So this actually concludes Unit 3. There's nothing else for you to actually learn. I have some notes in Moodle and some extra videos that you need to do that you can look at in Moodle to help you out. But now, once you finish, go ahead and start my Math++ assignments and start studying for your Unit 3 test. Let me know if you have any questions or concerns. Thanks.